Hello, and welcome to this GCSE Physics revision video looking at electricity. We're going to explain the properties of electricity such as charge, current, potential difference and resistance. We're also going to compare the series and parallel type circuits. So what is electrical charge? Charge is a physical property of subatomic particles, just like mass or density. Charge causes these particles to experience a force when placed into an electromagnetic field. There are two types of electric charge. We call them positive and negative. Positive charge is carried by protons, while negative charge is carried by electrons. Neutrons, as their name suggests, have no charge. They are neutral. Charge is measured in coulombs, with a single electron carrying a charge of 0.000000000000000016 coulombs. That's 1.6 times 10 to the minus 19 coulombs. So the number of electrons needed to create 1 whole coulomb of charge is 6¼ quintillion electrons. This is the number of electrons that flows past a point in a wire when the current is 1 amp. It's also roughly the same number as the number of grains of sand there are on all of the beaches in the entire world. Most objects in everyday life are uncharged. This means they have an equal number of positive and negatively charged particles within them.
Oh no, I've lost a neutron.
Don't worry, have one of mine, there's no charge.
We can charge objects, which means disrupting this balance or redistributing the charges. Simply rubbing one object against another will cause electrons to jump across due to the friction between them. In the case of a silk cloth rubbing a glass rod, electrons are rubbed off the rod and onto the cloth, leaving the rod with an excess of positive charge and the cloth with an excess of negative charge. The region of space around a charged object is called the electric field. Not quite, but I see where you're coming from. No, the electric field is what we call the three-dimensional space around a charged object. If another charged particle is placed within this electric field, the two charged particles will experience a force, and so they will be pushed either towards or away from each other. Like charges, such as positive to positive or negative to negative, will repel each other, while unlike charges will attract each other. You'll be expected to draw and interpret some electrical circuit diagrams. In order to do that, you'll need to know all of the circuit symbols shown here. It would be really helpful for you to pause the video now and quickly test yourself before I show you what each symbol means. So reading from the top, the first is an open switch. Then we have a closed switch. The open switch will stop the current flowing because it puts a break in the circuit and usually turns the circuit off. Closing the switch completes the circuit, allowing charge to flow. Then we have a lamp. Some people call these bulbs, some say lamps. Is there a correct name for them? An electrician will tell you that lamps glow and bulbs grow, which means that a bulb is something that you plant in the soil to grow daffodils or onions or other such plants. To be perfectly honest, it doesn't really matter what we call them, lamps or bulbs. As long as the person you're talking to knows what you mean, it's all good. Next we have a cell and then a battery. Notice the difference here, and this time it is important that you get these right. A cell is a single cell like this one here. Look at the company name, Duracell. I know most people would call this a battery, but it's a cell, a single cell. A battery is a number of cells joined together. A battery of cells, just like a battery of chickens is a number of chickens kept in a battery farm. This is a battery that looks like a cell. If we open it up, we can see that it contains individual cells. This next group of components act as resistors, which is why they have symbols based on that of the fixed resistor. A resistor, don't forget, is something which resists the flow of electrical current through a conductor such as a wire, in a similar way that water is resisted from flowing through a hose when the sides are squeezed. The symbols remaining represent a heating element, a fuse, a variable resistor, a thermistor, and a light-dependent resistor. Lastly, we have the symbol for a diode, which acts like an electrical valve, only letting current flow through in one direction, hence the arrow in the symbol. Diodes can also be made to light up, as shown by the two arrows on the symbol for a light-emitting diode. These components are used in most of our household lights, either the main ceiling lights or the small lights on our appliances, such as the little red light on the front of the TV when it's on standby. In order to use the various equations which describe electrical quantities, we need to make sure that we're using the correct units. This table summarizes the symbols and the units for each of the electrical quantities. If I show you the first row, which has energy using the symbol of E measured in joules with the symbol J, maybe you could fill in the rest of the table for yourself. So why not pause the video again here and challenge yourself? Can you complete the table? If you did have a go yourself, you can check your work as I show you the rest of the details. You'll need to remember all of these, so please do test yourself regularly. A quick quiz for you. What are the units of resistance and charge? The ohm and the coulomb. Circuit diagrams are how physicists draw electrical circuits using the standard symbols I've just shown you. Can you draw the circuit diagram for this circuit here? There's one battery, one switch and two lamps in series with each other. The correct circuit diagram might look like this. When the switch is closed, electrons flow around the circuit, carrying their negative charges and transferring energy from the battery to the lamps. Electrical current is a measure of the rate of flow of charge. In other words, current can be calculated as the quantity of charge passing a particular point in a certain amount of time. Or current equals charge divided by time, or I equals Q over T. We can use one of those formula triangles if you feel you really need one, although I'd highly recommend you learn how to rearrange these mathematical formulae for yourself. So remember how to use it. We cover up the quantity we're after, in this case current, and we're left with the charge over time. We can do the same for the other quantities in order to make these the subject of the formula. So covering the time gives us time equals charge over current, or T equals Q over I, and covering charge gives us charge equals current times time, or Q equals IT. Just remember that when calculating the current in a series circuit like this one, the current is the same in all parts of the circuit. The potential difference describes the energy that is being transferred to the component by each coulomb of charge that passes through it. It's measured using a voltmeter placed in parallel with the component. The units of potential difference are joules per coulomb, which has been given the more usual name of volts after the Italian physicist Alessandro Volta. Given the definition of potential difference and its unit, we should be able to determine the equation needed to calculate it as being equal to energy divided by charge, or V equals E over Q. The formula triangle, if you need it, is here, with energy at the top. Rearranging the equation to make each other term the subject gives charge equal to energy divided by potential difference, and energy equal to potential difference multiplied by charge. In order to understand resistance, I want to look at how metals conduct electricity. Charged electrons flow through a metal as they jump from one metal ion to the next, passing through with a flow rate or current equal to the number of coulombs per second, or amps. Each coulomb of charge is pushed through the metal wire by the potential difference equal to the number of joules per coulomb, or volts. The metal ions get in the way. They resist the flow of electrons. This resistance is measured as the potential difference needed to produce a current of 1 amp and is given the unit of volts per amp, or more usually the ohm, after the German physicist George Ohm. The equation to calculate resistance can be written as resistance equals potential difference divided by current. The formula triangle here may help us rearrange the equation to make current equals potential difference divided by resistance, and potential difference equal to current multiplied by resistance. The resistance can be thought of as the restriction of current, measured in terms of the potential difference needed to produce a 1 amp current. IV characteristics are a way of describing how a component behaves as a potential difference is placed across it. We can use a setup like this to find out how current through a component changes as we vary the potential difference across it. The shape of the graph can indicate the type of component being tested. If we plot the results using a fixed resistor as the test component, we find a proportional relationship between the potential difference and the current. The line is straight and passes through the origin. In other words, the ratio between the potential difference and the current is constant. And if we remember from the previous screen, this ratio is often how we define and calculate resistance. This relationship is called Ohm's law and can be better described if we rearrange the equation into the form V equals IR, because this clearly shows that current and potential difference are proportional. A simple wire will also obey Ohm's law in this way, provided that the temperature stays constant. The only difference is that because the resistance of the sample wire is likely to be different to that of the fixed resistor, the gradient of the two lines will also be different. Please also notice the significance of the lines in the bottom left-hand quarter of the graph. Here we can see that if we reverse the direction of the potential difference, the direction of the current also reverses. The gradient and general shape of the lines stayed the same though, for these two components. Swapping the component for a filament lamp, we see a different shape to the IV graph. A filament lamp is what most schools use in their physics labs, often held in lamp holders, or the older style household ceiling bulbs used to be filament lamps. With these lamps, the filament, which is a really thin tungsten wire, gets so hot due to the current flowing through it that it glows, producing light. The hotter the filament, the higher the electrical resistance, which is why we see a curved IV graph. The gradient of the line changes as the resistance increases at the higher temperatures. The final type of component we need to cover is the diode. Remember that a diode is like a one-way valve for electrical current. So at negative potential differences, the resistance is so high in this direction that the current is zero. Once the potential difference becomes positive, the current is allowed to flow through the diode with low resistance. There are two types of circuit that we need to be aware of. The first is the series circuit, where electrons flow around the circuit from the cell through all of the components and then back to the cell. In early experiments with electricity back in the 1700s, Benjamin Franklin, an American physicist, knew that charge existed in two forms, which he called positive and negative. He assumed that positive charges flowed from a region of positivity in the cell through the wires and back to the negative region. This description continued for almost 200 years and became the conventional way that people thought of electricity. Eventually, electrons were discovered to be the thing flowing around the circuit, and they were found to have a negative charge rather than a positive one. We now know that negative electrons flow around the circuit from the negative terminal of the cell to the positive. We call this description electron flow. Even though we know it's incorrect, most electricians and physicists still use the conventional flow model to describe electrical circuits and wire our homes. It doesn't actually make a difference to how circuits work as long as everybody uses the same system. A positive charge moving in one direction, don't forget, has exactly the same effect as a negative charge moving in the opposite direction. Don't believe me? Just ask a friend if you can give them minus £20. You'll be £20 better off. The battery or cell transfers energy to the electrons, causing them to flow through all parts of the circuit one after the other. If we increase the number of cells in the battery, the electrons receive a push from each of these cells. The potential difference of the battery will now equal the sum of the potential differences of each cell. The total energy transferred from the battery is shared between all components in the series circuit. So let's summarize series circuits for a second. The same current passes through each part of the circuit. So the current through ammeter 1 will equal the current through ammeter 2 and also through ammeter 3. The total potential difference of the supply is shared between all components in the circuit. So the total potential difference of the battery will equal the potential difference across each component added together. One more rule concerns the resistances of each part of the circuit. The total resistance will equal the sum of all of the individual resistances of each component. RT, or total resistance, will equal R1 plus R2 plus R3, etc., adding the resistances of each component in turn. With parallel circuits, the components are located on different branches of the circuit. The current flowing through ammeter D will split between the two branches to flow through ammeters B and C separately, before joining back up to flow through ammeter A. The rule, therefore, is that the total current through the whole circuit is equal to the sum of the currents flowing through the separate branches. In the diagram here, we can say that the current flowing through ammeters A and D will be equal, and that this will equal the current flowing through ammeters B and C added together. The potential difference across parallel components will be the same as each other. This will also be the same as the reading on the voltmeter across the cell. So the rule is that the potential difference across each component is the same as that across the cell. Or as shown here, the reading on voltmeter 1 equals that on voltmeter 2, which also equals the potential difference measured by V3. The final rule to remember concerns the resistors. The total resistance of resistors in parallel don't simply add together like they do in series circuits. Remember that parallel circuits offer the charges an alternative route to flow around the circuit, allowing a higher total current and therefore a lower total resistance. In fact, the total resistance of two or more resistors in parallel is less than the resistance of the smallest resistor. Imagine a road with a junction, but both routes lead to the same destination. There will be less congestion, with fewer cars on each of the two routes, allowing traffic to get where it's going much faster, i.e. there will be less resistance. A parallel circuit can be seen as two circuits overlaid on top of each other. The current will flow through both circuits at the same time. So thanks for watching. I'm not going to bore you with one of my old-fashioned electrical jokes. I've promised myself to make them much more current. Please make sure you subscribe and follow for future science content, new material or revision tips. You can contact me on my website plutoniumscience.com or Twitter at PU94Science, or just email me directly. Keep up the good work and good luck with the exams. Take care.